Hello everyone, my name is Steffen Bollmann and I'm a researcher at the University of Queensland and I analyze magnetic resonance imaging data of the human brain. And there is a large ecosystem of scientific software out there that enables our work. Here's one example of a tool we use, FreeCipher. It segments the human brain in different structures, generates surface of the brain, very, very useful. And there are lots of other tools out there that enable our work. And the problem is that there is a large variety of different tools and researchers have trouble using a lot of these tools. The first one being that most of these tools require Linux, but not every researcher has access to a machine running Linux. Then, even if a researcher has access to a Linux machine, the problem is the software is very often not in the standard software package systems and can't be easily installed. Then they are told to simply compile from source. But very often this is tricky and involves a lot of knowledge. And my own experience is that it doesn't always work. And when you change systems, also new problems come along. And a lot of my documentation looks like this, where I actually have to deviate from the official documentation to get the tool compiled. Another problem is that some of the dependent libraries are not available on the system or they're conflicting with other dependencies on the system. And because of this, when you want to reinstall your software on a different platform, it takes a lot of time because you usually start from scratch again, the problems are different, and it takes a lot of time. Finally, results change with different software versions of scientific tools and also the underlying system libraries. And this is nicely illustrated in that publication where they looked at the reproducibility of analysis pipelines and the dependency of the glibc library. So here they found that just the update from 2.5 to 2.18 changed the floating point position, and this then led to significantly different results in this pipeline. So this introduces problems for computational reproducibility, but also just adds computational noise that's unnecessary. So to summarize the problem statement that we had when we started with this project is that we somehow wanted to solve this problem. And here I just pick on the Python universe where it's often can be very tricky to get a Python system to run, a Python tool to run. And this is very representative for the problems we have in distributing scientific software. So at the same time, we want to solve the problem, but we don't want to create a new standard. So in this project, we did not want to aim to create a new package manager and solve all the problems in the world because that probably wouldn't work and we just end up with another standard. So to define what we really wanted to do is we started with a use case. So here this researcher wants to run an analysis of a tool called NiPipe, which uses Python 3, combine it with TGV QSM, which is still Python 2 and hasn't been updated yet. Then the researcher also wants to use FSL, which is a common toolkit, and the Mink toolkit to do this work. The researcher has access to a Windows 10 notebook. That's where the researcher would like to develop this pipeline on. Then, when everything is developed, test this on pilot data on a bigger workstation because it has more memory on Ubuntu 18.04. Then deploy that to a ROX CentOS cluster, analyze all the data, and download the results and visualize it on the Windows 10 notebook again, prepared for publication. And then finally also share this whole analysis setup with readers of the paper and describe it, what has been done so people can reproduce it. The problem is that the researcher will run into a lot of problems trying this. So first problem is FSL and Mink just don't run on Windows. Bad luck, they're Linux tools. When trying to install these on the old CentOS cluster, the researcher has access to, they are outdated libraries and it's very difficult to compile the tools on them. Mixing Python versions usually causes trouble. Compiling Mink fails because they're missing libraries. The researcher can't figure out what are these libraries and how to get them to work. And this whole software setup is not reproducible. Even if writing down every single step, the chances that one can repeat this exact setup are lower than winning an ARC DECRA grant. So since I said we want to solve these problems, but we don't want to reinvent the wheel, let's look at what is already available and what we could use to help. If you're familiar with the Python world, there is already a great package manager, Conda. If you're on a Debian system, a lot of the neuro tools are packaged in NeuroDebian. However, that doesn't help you if you're on CentOS. There are also great initiatives like the Characterization Virtual Laboratory, which already tries to solve a lot of these problems. So what we develop should tightly integrate into that. We also want to enable researchers to use the infrastructure they have access to. So it should run on Nectar Cloud locally. It should run on their workstation. It should run on their cluster. It should run on their notebook. And we would like to enable that. And then, of course, there's container technology like Singularity in Docker that could help us to solve a lot of these problems. So our project heavily will use containers. So before I go into our project, I quickly want to explain the difference between virtual machines and containers, if you're not familiar with it yet. So virtual machines, we had our hardware, we had a host operating system, then we installed a hypervisor like VirtualBox. And then in there, we installed a whole guest operating system like Ubuntu 16.04 with all the libraries, with all the things that it needed. And the problem is we ended up with quite a big image. And it also took a while to start up. And also it consumes a lot of RAM because you're emulating a whole operating system. So that's not that practical, but that's how it was used to be done a few years ago. And when the whole cloud computing came along, people thought about how can we make this process a little bit more performant. So what Docker and other container technologies are doing is they're using newer features in the kernel, which are called C groups and namespaces. And they allow us to separate processes from each other. So when we now install our toolkit, we don't need to emulate the whole operating system. We only need to virtualize the parts of the system that we actually need. And because of that, we end up with a very small container footprint. So the size is very small, can be easily distributed. The startup times are very fast because we're not booting an operating system. And also because of that, the RAM requirements are very low. So this enables us to run applications as if they were installed locally, but we can run them in a container and we can distribute them like a virtual machine. So to summarize, containers are, simply said, very lightweight virtual machines with a lot of advantages. We started this project at the Organization for Human Brain Mapping hackathon, where people from the community came together and people said, look, this current situation of installing neuroimaging software is so tedious and so frustrating. Is there anything we can do about it? And that's when we built NeuroDesk. So the design principles we had were that whatever we wanted to build has to run on Linux, Mac, and Windows. So we said probably the best way to do this is using Docker. We also have to run on an HPC. So for this, we need Singularity because Docker doesn't run very well on an HPC. It should be fully interactive, so we need a full Linux desktop interface. It should also be lightweight at the same time because it should be quickly to install, quickly to update. And also we wanted to reuse any library and repository that's already out there. This is what we built. We built an automated container building registry online on GitHub using GitHub Actions, where the community develops recipes using Conda, NeuroDebian, NeuroDocker, whatever it's available to build that software, contribute it to our repository. We automatically then build these containers and we store them in a Docker registry and a Singularity registry. And then we build the core tool, NeuroDesk, which then downloads these containers and manages these containers for the user and makes it transparent for them to use. So this is how it looks like. We use the module system on the HPC that gives us access to these different containers. And here's an example where I have two executables. One is FreeView, one is FSR-Math. So for the user, it just looks like a normal standard binary. But what it actually is, it's a wrapper script that then calls inside the Singularity container. And we manage all of these wrapper scripts for the user. So for the user, it just feels like it's natively installed. Now, one problem is that not every user has a Linux machine or access to HPC or access to CVL. So we wondered, can we help these users as well? So what we built is we build a single Docker container that contains a full Linux desktop that then has our NeuroDesk installation fully installed. And with this, we enable the whole setup on Windows and Mac by just using a single Docker container. And this is how it looks like for the user. The user just starts the Docker container. The Docker container starts up in a few seconds. Now the container is running. Now the user can just open a browser, go to a local port, and just open up this whole desktop environment in their browser. But one could also use a normal VNC player, so it's all the same technology. And then they can start working, start an application and do whatever they want. And we mount the storage through, so everything is transparent and it feels all very native. Then another important feature was that this whole image you see here is only 2 GB, but a lot of these software containers are much larger. So what we're doing here is if a user wants a certain application, we detect it and we pull that container live from the registry. So here we're pulling a 900 megabyte software container. Then we are executing this container. We're checking what are the executables in there. We make them transparently available to the user. And as soon as this is done, the user gets a terminal in a command line inside that container, and then they can start working. So that was the whole software setup. It would have taken multiple hours to compile that software, and here we just did it in a few seconds. And because we're using Singularity, also all the graphical applications work without any problem. And then another very important feature is that this whole setup is scriptable and reproducible because we use the LMOD module system. So here is an example where the user just tries to run FSL maths, but FSL is not loaded. When we load the container, we see which version we have actually loaded. And now we can run this command. And we see that it's a wrapper script inside that container. And now the user tries to run a different command, minkmath, which comes from a different package. Also, this has to be loaded. And when the user shows us where that library is, we see, okay, it's a wrapper script in a different container. Now, the cool thing is these two programs can now run next to each other on the same data, but they could have conflicting dependencies, but they're completely isolated in different containers. And that was one of the use cases that we definitely wanted to cover. So going back to our use case, we now solved a lot of problems. So our software is now completely reproducible. It's running in containers. We can run these containers on any system that has a Linux kernel and supports Singularity. We compile the tools for the users. The users don't have to worry about it. Python versions are now separated in different containers, so they're not conflicting anymore. The outdated libraries on the old CentOS cluster don't matter anymore. We just need Singularity, and then we can run whatever we need to get our software to work. And FSL and Mink are now usable on Windows, which wasn't possible before. And a new use case that we discovered while developing this is that now patient data can stay local. We don't have to transfer our patient data to a remote system to analyze it. We can actually leave it on that system. And that opens up complete new use cases for analyzing neuroimaging data in a healthcare setting. With this, I want to conclude. And we are all doing this on our free time. So we are very, very happy for contributions. If anyone thinks this is a cool idea and wants to help us, we need a lot of help in testing the software, testing the containers. We would love to have a Singularity registry in Australia to push our images to. Currently, we host that ourselves, but it would be good if someone would like to support us there. We would like to make the setup process easier for users. We're looking for more use cases. If you have a certain application that you'd like to see or a certain use case, approach us. And maybe we can get this to work. And we're also planning to extend this framework from the neuroimaging field to other fields like electrophysiology, because there we got approached by a lot of users who said, oh, we would love to have something like this in our field. Can you also build our applications in them? And we submitted an AIDC platform program call, and we hope that we get some support to develop this project further. I thank you for your attention and everyone involved in the project, and I'm very much looking forward to your questions. Thank you very much.